Hello there, Griffins. Mr. Milks here, video number 3, octet rule. This is going to be basically a video that is just kind of a fundamental theory video. We will get into the task next video. The octet rule itself, atoms want to gain or lose valence electrons in order to obtain a valence shell. This valence shell is 8 valence electrons. The only exception is hydrogen and helium. To be honest with you, for us it's hydrogen because helium doesn't react at all, so we won't see that either. But those are the two that can have a valence shell of 2 and be happy. We do call that a duet, by the way. Okay, duet instead of an octet. So you will hear that word from time to time. Ionic bonding. This is the complete transfer of electrons from the metal to the nonmetal, leaving both with a stable valence shell. And I have some pictures to show you what that looks like after you write that. Now you're going to pause and draw something similar to this picture, because here's the Bohr diagrams that show you sodium atom is going to lose an electron. It's going to get picked up by chlorine atom to form sodium ion, and notice what's missing. This valence shell is missing, leaving it with a full octet, and chlorine's now valence shell is full, giving it an octet. So now that I'm still talking and now I'm done, you can pause it and finish your drawing, and I will move on to the next one. Bam, there it goes. CaCl2, same thing here. Calcium is losing 2 electrons, but chlorine will only take 1, so therefore I need 2 chlorine molecules. And you can see that calcium on the right-hand side has lost its valence shell, giving it a new valence shell of 8, and chlorine's valence shell is full. Good. And just to spice things up a little bit, different kind of picture. This is an ionic bond with a polyatomic ion in it. So this is a special kind of one. You actually won't see me draw it quite like this, but this is the only picture I could find with a good polyatomic in there, with some of the hints and rules of how we draw ionics. So I see I have a calcium with a +2, a carbonate with a -2, and they will attract beautifully and like little tiny magnets and form an ionic bond. Okay, covalent bonding, a little bit different. 2 nonmetals, they share their valence electrons. Share is the keyword, ding, 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 and with another nonmetal, leaving both with their valence shells. And again, I have more pictures to show us how this is working. Okay, I have hydrogen, 2 times diatomic. So I have a hydrogen and I have a hydrogen atom. I add them together and I form this molecule. And you'll see that this is from one, and you see, whoop, that's this one. And this one down here, that's that one. And when I get those 2 electrons together, they form a bond, and that's what I draw here. So when we're all said and done with this, this is the end result that we're going to be able to draw, and this is the answer that we're looking for. And when we get good, we can start skipping those steps in the middle. We're going to need them for a little bit until we get good, and then we'll be able to move on. Remember, we practice until we can't get it wrong. We don't practice until we get it right. Okay? Okay, and my clicker just needs a little help, and now we're off to the races. Here is hydrochloric acid. I have the hydrogen and a chlorine at the top, and then I'm going to add them together, and here they're color-coded a little bit, where I have the red dot from the hydrogen with the 1 lone electron from the chlorine. When I get those 2 electrons together, they form the bond here, and then there's a 3-dimensional type of a picture showing us the actual molecule. So there's 4 in this particular picture, but they are sharing electrons to complete their octets. Okay, water, most common of the Lewis dots you will have to be able to draw for covalence. You will see this a bunch, and you will need to draw it religiously. What's missing on the left-hand side of this picture is the plus signs. I'm taking this hydrogen and I'm adding it to an oxygen, I'm adding it to a hydrogen. When I add them together and I line up those lone electrons, this, I can actually do it in red for you. This one's coming from that hydrogen, this one's coming from that hydrogen, and they fill in to give oxygen his 8 valence electrons, and then I can replace those with the dashes to show that they're bonds. That is how we share. Good. Metals. 2 metals. We had a metal and a nonmetal. That was ionic. We had two nonmetals, that was covalent, and the last choice is two metals. So a metallic bond is between two metal atoms. The metal atoms' electrons are what gets weird. They exist in what we call a mobile sea. And the picture shows a pretty good job of how things just get very convoluted with um, metals and their electrons. And because they form this sea of electrons. Like they really don't keep very good track of each other's electrons. They just let them out there, and they're really comfortable with the fact that, yo, my electron's out there, but I know my neighbor's electron's out there, so if I really need one, I can get one from them, and everything's cool. And the neat piece about this is why metals conduct electricity. This flow of electrons. Electrons are able to move through the solid, which isn't normally the case for most solids. So electrons are pretty much locked in place, just like protons, but metals, not so much the case. Okay, mobile sea is what we call that. Last piece, thermodynamics of bond formation. So this is another fundamental piece that we're going to touch on. You're going to see it just a few times, but you do really need to know this. This is actually very important. We will spiral back to this later on this year. When I form a bond, the atoms go to a lower energy state as the result of the bond. And here's the picture where I start at this energy level. There is a jump, but then I end at a lower energy level. Okay, so this is the kind of picture I need you to draw. We will go into these in detail later, but this is an exothermic reaction. Bonds forming releases energy. That's what you need to know. Releasing energy because they get to a lower, more stable place. That's why I've formed a bond to begin with. Okay, octets are more stable. The opposite is true. If I want to destroy the bond, I have to put energy in to break it. So therefore, all the atoms have a finish with a higher energy. We call this endothermic. Energy's going in. Okay? Good. And guess what? We just finished video 3. A little bit of theory and background before we get into the practical pieces. You don't have any practice pages, so do your Google Classroom assignment. Click that you're all done with everything, so I'm good to go, and we are good to go. See you tomorrow in class.